Okay. Yeah, the inverse formula, the derivative formulas that we derived, finding a bunch of derivatives using those formulas. I'm talking about for sine inverse and tan inverse. You'll probably need to know log differentiation or the alternative implicit differentiation, L'Hopital's one. Yeah. Nothing up my sleeves, guys. Okay. We are going to continue with related rates. And we sort of know the process already, so we're just going to do some examples. Kind of debating if I want to do examples the whole class or maybe move on to another topic. But we'll see. Depends on how exciting it is, because after you've gone through this a few times, it starts to get kind of boring. It's the same 6 steps over and over and over again. Related rates continued. So, as you might recall, this is when we have related quantities, and if quantities are related by some equation that we can determine, then their rates of change are also related. Kind of via that same equation, just by us differentiating that equation. Okay. Now, sometimes you will have a problem that describes some related quantities. They might describe a situation to you, and they might say, hey, we know how fast these quantities are changing. How fast is this other quantity that's related to them changing? And that comes down to what's called a related rates problem. Okay. Now, to solve a related rates problem, like I said, you do these 6 steps, pretty much always these 6 steps, pretty much always in this order. The only kind of hiccups you might have is that sometimes you skip step 2 if the equation for step 4 is provided for you. And sometimes in step 6, you might have to go back to step 4 to figure out some missing information. But other than that, you're pretty much going in this direction through these 6 steps all the time for any related rates problem. So once you identify something as a related rates problem, solving it should be relatively easy. The hard parts would be steps 2 and 4, usually. So you pretty much have to sketch, if an equation isn't provided for you, you pretty much have to sketch one and be sure to label it appropriately. We'll talk about that a little bit. And then from that sketch you have to come up with the equations. But everything else should be like plug and chug, just grinding through the machinery. And we did one example, kind of rushed through it last time, so let's just make sure we understand all the steps properly and go through a few more examples where we're applying these steps. So, and again, this is from I provided a handout for this. It is on the website. I also gave you guys a printout last time, but if you lose it, it is on the class webpage at the very bottom. There's a documents and handouts section at the very bottom of the page. Okay. So, let's just jump into it. Example 2. So, step 1 of any related rates problem is to read the problem. You need to figure out 1, that it is a related rates problem. 2, you need to figure out all the rates that they're telling you and all the values that they're telling you, because you might use that. 3, you need to understand the situation well enough to draw a picture of it if it's necessary for you to draw a picture of it. So reading very carefully is an important step. Consider it something that you have to worry about. And so, in example 2, we'll read, the length of a rectangle is increasing at 8 centimeters per second. Its width is increasing at a rate of 3 centimeters per second. When the length is 20 and the width is 10, how fast is the area increasing? So here they told you about some related quantities. These are the side lengths and the areas of a rectangle. And they told you about the rates of change of 2 of these quantities, and they asked you for the rates of change of a third. This is a classic related rates problem. Here are a bunch of things that are related. Here are how fast these things are moving. How fast is this thing moving? That's a related rates problem. So we've read. So 2, what I want to do now is create a diagram of the situation. And the diagram is going to, of course, be a rectangle, because that's what was described to us. I'm going to label these. You can label it whatever you want usually. So let's do length and width. You can do X and Y, nothing wrong with that, or whatever letters you want. Okay. Now, I label these with letters because they told me that the length and the width are actually changing. Okay? So they both have rates of change that are not zero, so neither of these are constants. Right? If they told me that only the length was changing, I will actually write a number here in place of W, whatever the width happens to be. Okay? But they're both changing, so I label it with variables. Okay? So that's basically the diagram. Okay. Third step is to now write down what we know and what we want. Right? Kind of set our intention, our goals here. And so far, we know the rates of change of both of these guys. We know that dl dt, and we know dw dt. Okay. So the length is changing at 8. They mentioned it is increasing. That means the rate of change is positive. There's a positive slope in play here. And the width is increasing at a rate of 3, so that is positive 3. Okay. Now, what do we actually want? We actually want how fast is the area changing, so we want dA dt. When, in the position at this point in time when the length is 20 and the width is 10. So that's it. Read the problem, understand its related rates. From that, I can draw this picture and fill out this information. Now, we move on to step 4, which is where we're going to write down our equation, the relationship that relates all of these guys. So here I want to relate the variables A, L, and W, and the picture of the rectangle should dredge up memories of high school geometry. So A equals length times width should be the formula that pops up, which is informed by the picture that you just drew and by what you know about a rectangle. So that's the relationship. Now the 5th step is to differentiate. Of course, it's going to be implicit differentiation with respect to time. What's the derivative of A? dAdt. Rate of change of A with respect to time. Derivative of this?
dL dt W plus L dW dt.
Product rule. Differentiate one, leave the other, plus leave the first one, differentiate this. At this point, we move on to step 6. Can we answer this problem? So what we need to find, plug in an answer. So at this point, I go to this formula and I see, do I have all the pieces to find what I want? dL dt, yes I know, that's 8. W is 10, L is 20, dw dt is 3. I seem to have everything, so I'm just going to plug in. dL dt is 8, W is 10, plus L is 20, and dw dt is 3. This gives me 80 plus 60, which is 140. And this is area. Now, again, I don't particularly care about the units, but this would be centimeters squared. That's the unit of areas, the square of a length per second. Yes?
How you're labeling each step right now, is that just for teaching purposes, or should we do that in our problems?
That's for teaching purposes.
Okay.
It would be nice. It would be easier for me to grade if you actually label the steps, but technically you don't have to do it.
Okay.
Cool. I really want to drive the point home that we're going through the same 6 steps all the time.
Gotcha.
So, I'd rather you write it down, but you don't have to.
And like on a quiz or test, do you have to write like the centimeters squared per second?
No, I
Okay.
don't particularly care.
It's like you just want the number?
Yeah.
Okay.
Units come into play if in the original problem, and this is another important situation where you should read, is if you're given a mix of units in the beginning, like maybe they give you some lengths in meters and some in centimeters, then before you do anything, you should convert all the units to the same thing. And yeah. But that's usually not going to be an issue. Like I don't particularly care about the units. The process is much more important to me, and chances are I'm not going to test you on it. I'm not going to throw in a unit trick. Let's move on. So yeah, 1 and 2 were pretty straightforward. That's just to get us in the groove. Let's look at example 3. So step 1, read. Step 2. Okay, so let's read. A 15-foot ladder is resting against a vertical wall. Suddenly, and without warning, Batman starts pulling the foot of the ladder along the ground, away from the wall at 2 feet per second. At what rate is the top of the ladder sliding down the wall when the foot of the ladder is 9 feet from the wall? So that is the situation. So what would you say the diagram is here?
Oh, right triangle.
Right triangle.
It's going to be a right triangle, right? Where over here, this represents the wall, right? Over here is the ground, and over here is the ladder. Okay, label the diagram. How would you label this diagram? Yeah.
Well, it tells us the ladder's 15 feet, so the hypotenuse would be 15.
Right. Label this 15. The ladder is not changing length. Do not label it with a letter. The ladder is always 15. It's a constant. You label constants by their constant value. The ladder is 15 feet. It's always going to be 15 feet. Label it 15. Okay, how else would we label everything else?
The bottom is going to be 9 feet.
No.
Would it be D? You label the bottom like DG, DT, or no? Just you just give it a letter.
This is a length. It's
Yeah.
not a rate.
You just give it a letter. So
Just give it a letter. Let's say X. Label this Y. You cannot label that 9 because it's not always 9. That length is changing. Batman is pulling this away. So this distance isn't always 9. It's moving. Okay? Similarly, this distance isn't always a certain value. It's actually shrinking. Because as you pull this away and this extends, this is going to shrink. So both of these lengths here are changing. We label them with variables. So in other words, I have a right triangle. The base is labeled X, and the height is Y, and the hypotenuse, which is a constant, is 15. 3. What do we know, and what do we want? And in step 1, we were supposed to read. And so we know that the foot of the ladder is being pulled away from the wall at 2 feet per second. So that means we know how X is changing. And what is that?
2.
2. What if I told you Batman was pushing the ladder towards the wall?
-2.
You would put -2, right? That's why reading very important, right? These little nuances can creep up on you. It is a +2, not just because the problem says so, but because from our picture we can see if you pull this that way, your X is increasing in length. Increasing means you have a positive rate. Okay? You can have the exact same picture, but just a switch in wording from away from the wall to towards the wall is going to change the sign here. Okay? So you have to be aware of your picture also as to how these variables are actually moving in the situation, right? So the x is getting bigger, the y is actually getting smaller, and knowing that is going to be important. That's also going to be important for knowing whether your answer makes sense or not. So what we're after here is the rate of change of y, and from this situation, what would you expect that answer to be, positive or negative? You would expect it to be negative, because as that extends, this decreases. So y is a decrease in quantity. So just by examining this picture and comparing it with what you read in 1, you automatically know the rate of change of this is positive, the rate of change of that is negative, and that should be something that's always in your mind. If you go through the problem and you get a positive number at the end, you know you're wrong. Okay. All right. Now, so that's what we know, and that's the only rate we know. So what do we actually want? Well, we want to know what is dy dt doing when, in what situation? What's the condition here?
When x equals 9.
Okay, when the foot of the ladder is 9 feet from the wall, according to my picture, x describes the length. The foot of the ladder is from the wall, so this is when x equals 9. Okay. Moving on to step 4. Now we're going to have to come up with an equation that relates the variables that I care about. What would you say relates x and y here?
Pythagorean theorem.
Pythagorean theorem. So my picture is a right triangle. All the values that are filled in are the side lengths of a right triangle. We know have a nice equation that relates all the side lengths of a right triangle. So this picture now gives me an idea as to what equation I can use, and in this case I would use Pythagoras' theorem. And that would tell me that x squared plus y squared is equal to 15 squared. That's the relationship. 5. I am now going to differentiate this with respect to t. Okay. What does that mean? Differentiate with respect to t, what do we get? Where does it come?
To the
Huh? So that's the x dt. Zero. That's a constant. Okay. Now, one of the dangers in mislabeling is that, let's suppose someone labeled this z, right? Then over here, they have a z squared. Then right here, they have a 2z dz dt. And so it's going to feel like, wait, there's something missing from this problem. The real thing is that your dz dt was 0, and you actually don't have to worry about that. But I find a lot of students might end up in a situation where they now have this extra variable in play and they don't know how to deal with it. You can avoid that situation entirely by just labeling properly in the first place. If it's a constant, label it a constant, because once you do step 5, all constants get wiped out and you don't have these extra variables that you now have to think about. Wait, what is this z right here? So that's the point of labeling things by constants. So you can just reduce the amount of information you have to process down the road. So far we have this. In fact, we can divide both sides by 2. That's not going to be an issue here. But now we start to move on to step 6. Step 6 is going to be the phase where we plug in and solve. Okay, so what do we know now? We know dx dt is 2. We know x is 9. this is the guy I want to find, dy dt. We know y. Oh wait, we don't know y. What's y?
12.
Huh?
12.
12. Now, how do you know it's 12?
Pythagorean theorem.
Yeah.
Right, you go back to step 4. Notice here, we need y to plug in. Right? So this is describing that situation where when you get to step 6, there's some missing information. How do you find that information? You go back to step 4. Right? Now in step 4, we have this relationship. We know that x squared plus y squared is 15 squared. And we know that our x is 9. Now you can just solve for y directly here, but it's nice to realize a pattern here. Notice that your 9 is 3 times 3, and notice that your 15 is 3 times 5. Now why did I point that out? What's this pattern called that I'm obviously referencing here? When you guys told me 12, did you actually calculate that? Or?
Well, like I just know like one of like the rules for Pythagorean theorem is like it's gonna be 9 squared plus 12 squared always equals like 15 squared.
Okay. Well, it's usually memorized at a lower level. It's called a 3, 4, 5 triangle. Right? So in any right triangle, where one leg is 3 and the other is 4, the other side is always 5. And we know that this works proportionally. So if I multiply this side by 3 and that side by 3, then the resulting side here multiplied by 3. So you can get 12 that way as well. Okay? So patterns like this, right? You have the 3, 4, 5 triangle. Another popular one is like the 7, 12, 13. But in any case, ultimately here we find that our y is going to be 12. Right? So this problem is already a little bit more sophisticated. We get into the situation where I said labeling can become an issue, so make sure you label things properly, as well as sometimes you get to step 6, you might not have all the information. Don't freak out. You can find that information by going back to step 4. Now that we've found that, we can continue the problem. Maybe I want to continue. Now we can plug in. Our x is 9, dx dt is 2, plus our y we now know is 12, and dy dt we don't know, that's actually what we want to find. So again, we can kind of divide this. That's 6. Divide both sides by 2. Can again divide both sides by 3. And so here I have 3 plus 2 dy dt equals 0. So then dy dt equals minus 3 halves. And it's in feet per second. Again, I don't really care, but feet per second. And here you would realize that we actually have the negative sign in our answer, which you should think to yourself, okay, that makes sense, right? So it makes sense that there's a negative. Because according to our picture, the y is actually decreasing. Any questions on this one? Yeah.
I know in physics, it doesn't matter, like, if the negative and positive, like, makes sense in what we think, because, like, negatives and positives are arbitrary, and, like, the math works out, and you just, as long as, like, the things that should be opposite signs are opposite signs.
Sure,
So,
yeah.
like, does it,
But they matter in terms of the convention you're using. Like if you think of up as the positive direction and down as the negative direction, it can actually change how formulas work themselves out.
yeah, but, like, as long as up and down are opposite signs,
Yes,
like,
that
they
should be
work
fine.
out.
Yes.
So, like, if we were to do it wrong, but it was the opposite, like everything that should be opposite signs was opposite signs?
No, there is no wrong. That is something that kind of, it's not a matter of convention, the signage in this case, right? Because the derivative directly correlates to the slope of a line. And telling me that the slope of a line is positive versus negative can be factually wrong. It's not like, oh, it's a convention that we do. Right?
So you care, that's what you're saying.
Yes, the sign here of a derivative, yes, you definitely care. And even in physics, you would care about that. It's just that in physics, you care in kind of a fluid way. You kind of care by the convention you happen to be setting up in the problem. However, for calculus, the convention of positive goes with increasing slope, negative goes with decreasing slope, is a convention that is taken throughout the entire course at all times without stating. But yeah, there are situations in physics where you might see the downward direction as considered positive and the upward direction as considered negative, but the simplest example of that I can think of actually shows up in like differential equations, or when you're examining systems that are spring mass systems, like the mass oscillating at the end of a spring. When you're setting that problem up, they usually set up the downward direction as positive, and that's because to solve that problem, you have to set up what you call a differential equation. And in that differential equation, the sign change that would occur would make the problem go from very easy to solve to very hard to solve. So they pretty much say, okay, let's just pretend this over here is positive and set up the whole problem that way, just because down the road it's going to make our calculations easier. Right? So that's a thing you can do in physics. But in calculus, no, we're always considering increasing positive slope, decreasing negative slope. There is no argument about that. Okay, let's look at another one. I guess we'll just keep doing some examples here. Let's actually jump around. Problem 7 is a nice problem. Because it illustrates another kind of standard trick that people can apply in this situation. So let's jump to that. And pretty much any problem, any example here that I skip, consider it as a part of your homework to actually go over those problems on your own. So I'm going to jump to problem 7. And maybe we might also do problem 8. Yeah, so as far as what would come on a test is concerned, right? Like problems like 1 through 6, I could like throw those on a quiz. Problems like 7, 8, 9, 11, and 12 are like problems I would throw on a test. They're a little bit more hefty. They go through the same steps, but if you want to practice for like a test, those would be the ones I would go to. They're not. It's not that they do something radically different, but they're not as simple to set up. So let's actually jump to example 7 here. Step 1 is to read. A water tank has the shape of an inverted circular cone, has a base radius of 3, height of 9 meters. It starts out filled with water, but the water is leaking from the bottom of the tank at a rate of 2 cubic meters per minute. For some odd reason, we want to know how the radius of the remaining water is decreasing, how fast that's decreasing, when the radius is actually 1 meter in length. Please determine this rate. And here we are giving you an equation. The volume of the circular cone is given by V equals 1/3 pi r squared h. So we have an equation, but I'm going to want to draw a diagram anyway, and then we're going to see why in a second. Can go through, you can actually fill out a template, because this problem is going to go through the same few steps. So that great. You know if it's a related rates problem, you know exactly what's coming. Going to do this, then that, then that, then that, then that. And by the time we get here, everything should be solved. Okay. So I'm actually going to draw a picture here, and we'll come back to it. You'll see why it's necessary to draw a picture here, even though they gave us the equation. Let's look at the situation. There's an inverted conical tank. We're going to make some changes to this diagram over here, so kind of leave some space over there. All right, so this is kind of the situation. There's water in this tank. It used to be full in the beginning, but at some point, water started leaking out of this tank. Okay. And we know that the dimensions of the tank. The radius is 3, right? So if I look at the center here, that is 3. That is not changing, so I'm going to label it a constant. I also know the height of this tank. That is 9. And these are in meters. That is also a constant. That is not changing. What is not constant in this case is if we're looking at the water inside the tank. Now, inside the tank, things are actually changing in terms of the height and the radius, right? Right? So if I call this R to be the radius of the water in the tank, and I can call the height H. Okay? So that would be the labeling for this situation. And we are told that our V equals 1/3 pi r squared h. Something like the volume of a cone. I'd probably give you that formula if I'm asking a question like this. It's not something you hear every day. Okay, so you kind of set that up and like, okay, cool. All right, they actually already gave us the equation. So we kind of even know what to fill in over here. You might think everything is hunky-dory, but let's actually just go through the process here, see what's going to happen. What do we know so far? The water is leaking out at the bottom, da-da-da. How do you write that down as a statement?
D, yeah.
Come again?
dH dt. B2
Is?
2.
Okay, no. Why not?
Negative.
Oh, negative.
Still no. Why not?
dV dt.
dV dt. How do you know that? Because water is volume, and the units is meters cubed. Meters cubed does not describe a length. The height is a length. Right? Read. Step 1, super important. Right? This rate that they gave us is in meters cubed per minute. Cubic units represent volume. Okay? So that 2 here is not referring to a height. So yes, the volume is decreasing at 2 units per minute. Okay? So that we can pick out. And so now, that's what we know. Here's what we actually want. We want to know dr dt, right? We want to know how the radius of the remaining water is decreasing when r equals 1. So that's what we know, that's what we want. So now you might decide, okay, let's just continue this process here. And what would we have over here?
dv
Okay, so that's the equation. If we start to differentiate it, what are we going to realize? What would this be? Differentiating this.
dv dt.
I'm writing this in red for a reason. You're going to notice what's going on. What's going to happen? What is dv dt here? Differentiate this side with respect to t, what do you get?
You're gonna end up getting dh dt, which we don't know.
Right, but what? Just write out what would you get?
Um,
Let's assume you're in a test and you just decide to plow through the steps. At this point, you should realize something's up. I want to know what you would get here to realize something's up. Okay, so what would we get here?
pi third, 2 pi thirds dr dt.
2 pi thirds
No.
r dr dt
Yeah.
h
Plus 1/3 pi r squared dh dt.
Okay, so what's the issue here? Well, you kind of mentioned it before. The dh dt is an issue. See, I do not have any information about the dh dt. I know about v, and I know I want to find r. What the heck is dh dt? So, to figure that out is where we're going to go back to our diagram now and try to somehow find a relationship between r and h. Okay? So now the idea that we're going to get is maybe we can find a relationship between r and h, and so I can replace that h with some function of r. Right? So that's the very typical way to apply this situation. And here's the trick. You pretty much look at this, you take a slice here. Right? Taking that slice ultimately would give you a picture like this. If you just take a planar slice through this thing, you would end up with 3 here, you'll end up with 9 here, you'll end up with r here, and you'll end up with h here. Now, can anyone tell me a relationship between these two?
It's 1 to 3, and r is 1, so it's just 3.
Right, it's what we call similar triangles. They will be proportional. So that means the height over base of the big one is going to be the height over base of the small one. So 9 over 3 is going to be the same as h over r, because similar triangles means that the sides are proportional. So the height of the big triangle over the base of the big triangle should be the height of the small triangle over the base of the small triangle. And then we end up with that relationship, which now I can actually solve for my h. I will get my h, I can actually write as 3 times r. And so now what I'm going to do is I'm going to come up with a slightly different equation. So here, by applying similar triangles, I end up with the fact that v is going to be 1/3 pi r squared times 3r. In other words, for this particular cone, this one in particular, my volume will be given by pi r cubed. And so now I can move on to step 5. and start differentiating. And at this point, I actually have all the information I would need. I know that dv dt is minus 2 equals 3 pi r, I know is 1, and dr dt is the guy I want to find. So this means your dr dt would be minus 2 over 3 pi. And technically this would be meters per minute, but I don't actually care. It's also worth noticing that this is a negative sign, which means radius is decreasing. And that seems legit. So I kind of assume I made the right calculations and just move on to that. So yeah, we'll do that. I'd probably try the other examples. Ask me questions if you have trouble figuring those out. But again, it's really the same 6 steps, but different problems can have little nuances and tricks here and there. I think we kind of covered all the main tricks. So things like similar triangles, going back to step 4 if you get stuck at step 6. In the case of problem 11, you can skip step 2, so on and so forth. But yeah, I'd really practice the others, especially from like 7 onwards. And we'll probably stop there. Next time we'll talk about linear approximation, I think is our next topic.